So thank you everyone for staying up until afternoon to listen to my talk. I'm very honored to be here. And so quick introduction about myself. I'm a last year PhD candidate from MIT Operations Research Center. And my research focuses, broadly speaking, on using machine learning models for climate change adaptation. And I actually have worked on hurricane forecasting, so similar to the previous speaker, but that's not what I'm talking about today. Talking about slightly different project on flood prediction. So kind of the motivation of why I was interested in flood prediction was a rather personal one. Back in 2022, I was studying, and I was outside of classes, and then there were lots of students who were fundraising for the Pakistan flood. I don't know if you recall, but a third of the country was underwater for several months. And given that it was already a very underdeveloped country, it just put lots of people in poverty. So there were lots of policymakers gathering around MIT and Harvard and discussing what can we do as collective community to help resolve certain countries that are more at risk for climate change implications. And not only for it's relevant for these underdeveloped countries, but also in the United States, it is forecasted that overall there is a 25% increase of flood risk across the country. So we have to do something because these natural disasters are extremely devastating for communities, but also extremely expensive. So just 40 billion damage caused from the Pakistan flood alone, and on average in the U.S., every time it happens when there's a flooding, it's billions of dollars of damage at least. So kind of the general goal of all of the projects that I have been working on centers around using machine learning and optimization tools for adaptation, to build resilience, and aid sustainable development. So I guess just a quick kind of, just putting things into context. So why do we care about meteorology, and why do we care about using machine learning for meteorology? And why now? So obviously, like many other fields, AI is taking off now because of the computing power thanks to NVIDIA and other big tech companies, and also data availability with all of this trend towards open source, etc. And finally, we're seeing tremendous growth across processing techniques across multiple dimensions. In particular, computer vision has developed a lot in the past, and natural language processing has been the hot topic for several months, or for the last 2 years. And finally, we're dealing with time series data, which is really kind of a timeless topic that many, many people care about across different domains. And it is essentially the kind of the parallel progress across all of these fields that allow us to do something called multimodal machine learning, which is really about data synthesization, which is how can we leverage data across different formats and domains and modalities to make the best prediction possible. So the project that I'm kind of talking about right now, today here, is about using a multimodal approach to forecast flooding events. And I guess many people have worked on forecasting flooding events, especially insurance companies. So how can we do this differently? So I guess my previous experience has been on weather forecasting, and flooding by itself is kind of, it's a physical phenomenon. So one of the tasks that I kind of decided to challenge, which is can we extend the forecasting horizon from maybe days, hours of days to multiple years? So then that can give us enough time to do preventative measures. And secondly is that previously, or rather a lot of these machine learning for meteorology models, including the ones that I have worked on, we use a lot of satellite image data. And yet, at the same time, we see a lot of growth in natural language processing. And also, language data is an extremely valuable data, which is very, it's very easy to use, and it contains lots of information, and it's unstructured, which means that collecting data is much easier than structured data. A little bit more difficult to process, obviously. So, kind of, first, we try to understand a little bit of the existing approaches to flood risk mapping. And as I mentioned before, the models typically separates into near-term forecasts and longer-term forecasts. So near-term risks, they typically form a physics-based model. They're called hydrodynamical models, and they're basically modeling, really simulating how the water system goes, and therefore, based on rain, precipitation, etc., they try to forecast flooding risks. The downside of this approach, obviously, is that they're highly local, and also error propagates as we stretch the forecasting horizon to, say, years. The other kind of more longer-term risks, which are typically used by insurance companies, they're more crude estimates, and they typically just look at historical risk. And that put us in the situation where we are unable to, or rather difficult, to incorporate climate change risks. So I mentioned multimodal machine learning, and how do we do this? So basically, as I was thinking that when you think about a lot of these hydrodynamical models, I read some papers. I do not claim myself to be a physicist nor expert on the field, but basically a lot of the times people take into consideration of the location of lakes, rivers, and how close certain locations are to water sources. So at the same time, if you look at the Wikipedia page, there is a geography section about places. And these are open source, crowdsourced insights about locations. And also, they describe a lot of information such as lakes, and if a place has a harbor, or just basically, they contain a lot of the geographical insights about locations. So basically, the task of this work is on, can we extract useful information using vastly available open source Wikipedia language data to describe the geographical features about locations. Obviously, Wikipedia is not the only source of geographical information given in text format, but I'm just using it as a very basic example here. And obviously, it would be interesting to extend this work to also include satellite images. But as I explained before, part of the goal of the project is to explore different formalities of data that are rather underexplored. So we're working on comparing results with satellite images, but the results are not so, we're not so confident to kind of show in this context. But nevertheless, kind of very quick summary of the methodology here. So basically, we have historical flood data, which is given in tabular time series format. And we used also terrain data, which are given in text format. So the text information processing, we've tried 3 different models, 3 different approaches. So everything is based off DistillBERT, which is open source language encoding, transformer-based open source model. We've tried fine-tuning it, as well as some transfer learning techniques. I think the details of the technique doesn't matter so much, but basically, what we have found from the results that I show here is that, first of all, when you think about forecasting flooding from 1 to 5 years of horizon, we're seeing that machine learning models do show some, interesting results, that we have pretty reasonable scores that basically shows us that there is the potential of doing longer-term forecasting using a machine learning approach. And secondly, we do see that when we added language data to the traditional statistical data, we see the degradation of performance over the years decrease slower when we added additional information. And also, generally, they tend to perform slightly better than using only, for example, statistical data. That's all I have for the presentation. But basically, what I think is interesting is that, so I have worked on hurricanes and flooding, as I mentioned. But really, I think that what is very interesting is that when we think about using machine learning for meteorology and for thinking about climate change adaptation, there will be very interesting applications across different, first of all, in terms of natural disasters and extreme weather conditions. The similar approach could be replicated for droughts, wildfires, earthquakes, storms, and that would allow us to design different systems for more preventative measures, for example, agriculture domain, real estate, and energy planning, etc. Thank you very much for your time. Happy to take questions.
I see a question all the way in the back.
Yeah, hi, thanks. My name is Sophie. Thank you for that work. For me, it's definitely very interesting. And I have two questions, actually. One is more technical. That will be, do I understand correctly that flood and hurricanes, these outcomes you predict just binary labels, so it's not just like a geographical map where a risk is high or so, but it's rather is like a one-to-one mapping on is this place at risk of flooding, yes or no? That would be question one. And then question two is more taking it a bit further. I was just curious if you have encountered work or maybe even plan on doing it yourself in this explainable realm, right? Because on the one hand, it's very interesting to understand, hey, there might be a risk of flooding in place A, but then you also want optimally get to these interventions where you say, hey, but if we create water retention or we build back natural flow of this river, XYZ, right, then we can actually prevent that from happening. Yeah, and I'd just be interested on your take on that.
Thank you for the question. So I guess to answer your first technical question, for this work, I'm predicting the binary classifier to predict certain, so I split into geographical grids, so 1 degree by 1 degree grid on Earth, which is 10 kilometers squares. And I'm predicting the risk of a certain place having a major flood in the next n years. So the n is 1 to 5 years. So that's for flooding event. And for hurricane work, we actually did just intensity and track forecasting for hurricanes. So that's more regression task, but not, it's for 12 hours in advance. So that's a very different project. It's more short term, and this one is more long term. And the second, to your second point about explainability and to do preventative measures. So in my personal opinion, we have done some work on explainability to think about what features are important to forecast the risk of flooding. So hopefully we can figure out what are the early detective markers to think about major flooding events. So that is to the extent of how I think machine learning can help in terms of explainability part. In terms of how to prevent a major flood, so I was talking with more urban planning people, and I think that perhaps drainage system is the most effective way to prevent flooding in cities and urban areas. So perhaps it would be more of a, I see it more as a collaboration from risk mapping perspective, which is more technical and more what machine learning models can help. And in terms of actually actionable items, perhaps it's more reasonable to take a collaborative approach. Yeah.